All right, finally, composing and decomposing functions. I get a little excited about this one because this is the sweet spot for the arrow diagram. It's what it does better than anything else. And so that is the tool that we are going to go to. You have some additional notes on your page, more than what is here. But the way that we're going to start this out is by making arrow diagrams for each of these existing functions. Now, this first one, f of x, is a combination. We said it's not, the arrow diagrams are not the strong suit for combinations, but we can make them work in this case. And basically, we're going to put the whole thing up here. So for the function f, which we'll do f here in blue, the arrow diagram just looks like that. We actually don't even need the x there to represent what that arrow diagram is. It just says that whatever comes in, you're going to square it. You're going to also multiply it by 3, and then you're going to add those two results together. Okay, we'll do g of x in red. It starts with an x there. We'll put that there temporarily. The first thing that happens is a sign change that puts a negative in front of the x. Then we are adding 2 onto that. And then that whole thing ends up in the denominator, which was our fairly recently acquired reciprocal function, or flip it over function, whatever we want to call that. And so those 3 arrows together make the function g. Okay. So there is g, and I oftentimes will point out that it's g is from here all the way to there. That's how g is accomplished. We just break it down into bite-sized pieces there. Okay. And then finally h. H we'll do in green. H starts with the x, and we add 1 onto it, and then that gets stuck into the power of 10. So these 2 arrows again together represent, let's see, okay, that'll work. 2 arrows together represent the function h. And again, we don't really need the x there. Now I'm going to do some tricky things with my smartboard that you wouldn't necessarily be able to do otherwise, but it should speed the video up here a little bit anyway. So I'm going to group those things together. Oh, I already grouped them together. What I am going to do is something called an infinite cloner on that, and I'm going to infinite clone this as well as this. Now in your notes it says that f, we say f composed with g, some people say f circle g. Those are both understood, but it's interpreted this way, right? So f of g of x, which the x is where everything starts. So we are supposed to start with an x, and the first place the x goes is inside the g. Well, this is g. So the x is going to go into g. It's going to get an output that is g of x on the far side, and then that output is going to go into the function f. So we put the f arrow at the end. And then we just follow along and see what we get. Opposite of x plus 2 was cleanly written as 2 minus x. Flip that over, 1 over 2 minus x. There was g of x. And now this goes into both of those sets of parentheses, and I get 1 over 2 minus x squared plus 3 times 1 over 2 minus x. Okay. We'll deal with simplification considerations at another time, but this is it. This is f circle g of x. Okay. Sometimes we put that f circle g in parentheses, sometimes it doesn't have to be. Just recognizing what it is in the context and that we're not writing the word fog. Okay. So that, like I said, is it. the arrow diagrams do that nice and clean. Okay, so let's take a look at this next one. We maybe even don't need to take this intermediate step. We know that the first thing that's going to happen here is the f. Okay, so this time you chose the variable t. Fine, we'll start with the t. They want us to start with the t and put that first of all into f. So here is my arrow for the function f, and then put that into the function g. Here is our arrows for the function g. Okay. So we do what it says. T squared plus 3t comes out of there. This says change the sign on that, so that's going to be negative t squared minus 3t. Add 2 onto all of that, so there's negative t squared minus 3t plus 2. And then it says flip that thing over, so you get a 1 over negative t squared minus 3t plus 2. This is g circle f of t. Nice and easy. Let's see, which is good. Hopefully this will be a little shorter video. They've been getting a little bit long. Okay. Ooh, that one looks weird. H of R. So it says start with an R. I understand that part. Okay. So we'll start with the R. And the first place R goes is into the first thing that we see connected to it, this one right here. So remember again, this is H of R. So the R goes into the H. All right, here is an H. And then the output of that goes into H. So we need another copy of H. And we'll string those all together, and that should be H of R. So we get an R plus 1, 10 to the R plus 1, 10 to the R plus 1 plus 1, and finally 10 to the 10 to the R plus 1 plus 1. Okay? This is H of R. It's a funny looking function, certainly a lot more going on than what we have taken the time to look at. I don't have any idea what that graph looks like. It looks like a super exponential or something like that, probably climbing very, very fast. But that gives us a fairly easy, using the arrow diagrams, it just step by step tells us exactly what it is that we need to do. Okay. Now, the reverse of that is the idea of a decomposition of a function. So when we're decomposing functions, we're trying to come up with the functions that were put together through composition to get something new. So, in order to do this process, what we're going to do is we're going to make an arrow diagram for this final result. This says this is the composition of 3 different functions. K composed with M composed with N of X. So we could also write this as K of M of N of X. Okay? And use lots of parentheses. So that means the same thing there. Let's start with our X and see if we can figure out what happened to it. The X, first of all, got squared. Okay, so there's my first arrow is squared, and then we had a negative sign put in front of that, and then we added 5, and then that 5 minus x squared ended up in the denominator, so it got flipped over, and then it got multiplied by 3, and then finally I added 2 onto the whole thing. Okay. So there are a number of arrows involved in this, 1, 2, 3, 4, 5, 6 of them, that I can see, and it wants possible rules for k and m and n. Well, here's the thing. If it wants it broken into 3 parts, then let's break it into 3 parts. And I've got lots of options of where to do that. I could do it nice and evenly and say I'm going to break it here and here. And if I do that, the first thing that happened was the n. So these 2 arrows together must be the n. And then it went into m. So I could say these 2 will be the m. And then finally, I will have these last 2 be the k. Again, not the only way I could have done it. I could have made those 2 blue vertical bars anywhere that I want. So what are my functions? Well, k of x. If I look at the arrows there, if I started here with an x, it would say 3x plus 2. So k of x is 3x plus 2. M of x, if I started with an x there, it would say, okay, x plus 5, and flip that over, that's 1 over x plus 5. So that's 1 over x plus 5. And then n of x, if I started the x there, that's x squared and the opposite of x squared. So this is just negative x squared. So you can play around with splitting it in different places and see what the different functions are that you might be able to come up with. But this will, this combination of 3 here will definitely satisfy the question that's being asked. So these are possible values for k of x and m of x and n of x, and if I compose them in that correct way, or in the way that's prescribed in k circle m circle n of x, then I will end up with the target function there. Okay. All right, so all of this stuff we've been talking about domain along the way as well. So the domain considerations here, we know that v of t has a domain where t cannot be equal to 0. And then I've got a w of z, which this function notation just tells me what the variable is in the rule. This is z squared minus 9. And I want to find v circle w of x. Okay, so that means I'm going to start with x, and first of all put it into w. My w function I'll do in blue is squared and then subtract 9. And my v function, I'll do that in red, that's just the reciprocal function. Okay. So v circle w does the w first, okay, and then puts the v at the end of it. And so at the end of the 2 blue arrows, I know I'm getting an x squared minus 9, because it wanted me to start with an x. And so this is 1 over x squared minus 9. Okay. With this function, this red one, the reciprocal function, had a domain restriction that said that x cannot equal 0. The question is there anything that I might have started with over here that would have made a 0 come out the end? Well, let's see. In this case, I'm going to be able to do the 9 and this. I think we talked about this before, that is a plus or minus square root at that point. We also could have done it by some factoring and things like that. But if I applied that to the 0 that I'm not supposed to be able to get out of there, then 0 plus 9 gives me a 9 there, and plus or minus the square root of 9 is plus or minus 3. So for this composition of functions, I can't have x be, I can't use an x of 3 or negative 3, because starting with those numbers would end up giving me a 0 right before I had to do the reciprocal function, and I'm not allowed to use a 0 in the reciprocal function. So because what went in there was quadratic, there were actually two possible ways that I would end up with a 0 there. So there are things like that that can happen with the domain. It's actually, I can start this problem with an x equals 0, and I won't have any issue at all. Okay, my issue is starting with a number that's going to eventually put a 0 in the wrong spot. Okay, so that's the kind of thing that we have to look for. Okay, and how that works out with the arrows is not always exactly the same or as easy to do maybe as this one turned out to be. But just to be aware that you've got to be sensitive to each subsequent function's domain restrictions and make sure that what's coming in doesn't end up violating one of those domain restrictions. All right, that's what I've got to say for composing and decomposing functions, and we will see you in the next video.